So today I want to take a look at automobiles, and really at automobile engines more than anything else. I did put up problem set 9. It's going to be one of the first semesters in a while that I've gotten to all 10 problem sets. I'm sure you're thrilled to hear that. So problem set 9 is up there. It's all about air conditioning and climate control and stuff. So it's material that I sort of finished up last week, and it's due a week from Wednesday. So not right after the break, but a little after the break. All right. So automobiles are, in many respects, the opposite of air conditioners, the automobile engine anyway. The idea is this, that in air conditioner we saw that you can move heat the wrong way if you're willing to invest some work in the process. And even more importantly than investing some work, if you're willing to invest some order in the process, commit some extra order and create more disorder as a result, you can do it. You can move heat the wrong way. Automobile engines are an example of a heat engine. And I should say, an air conditioner is an example of a heat pump. I've used that term before. So a heat pump is a system where you move heat from cold to hot while bringing in work to make this happen. And when I say you bring in order instead of work or in place, Al, can I have earmuffs too? Oh, sorry. Anyway, instead of bringing in work, you could just bring in order and turn. Thermal energy is disordered energy. Work is ordered energy. The order is the key thing in the work. And in principle, you can bring together order and any form of energy, including thermal energy. Together, that gives you something to work with. Let me step back from that, though, and just re-emphasize that a heat pump moves heat the wrong way, consuming work and turning out thermal energy as a result. A heat engine is the reverse of that. It lets heat move the way heat naturally does flow, from hot to cold. And in doing so, it diverts some of that heat and turns it into work. So it's the reverse. Like why? And so why can you do that? Why can you take heat flowing from hot to cold and divert some of it and turn it into work? It's because if you simply let heat flow from a hot object to a cold object, just freely, you touch a hot object to a cold object together, the heat flows and it creates a lot of entropy in the process. The bigger the temperature difference between those two objects, the more entropy is created, the more disorder is created. You're mixing hot and cold. These are very different things. And you bring them together, you're making lots of mixing, lots of disorder as a result. And you don't have to create that much disorder. The law of entropy says you can't make disorder decrease in a thermally isolated system, but you don't have to make tons of it just willy-nilly. That's wasteful. So under the law of entropy, you can reduce the amount of entropy you create in letting heat flow from a hot object to a cold object and save a little of it and actually turn a little of it into work. So that's the basic idea. And to illustrate this, we got lots of heat engines around. So whole collection. Thanks, Al. One classic heat engine, a lava lamp. I don't know whether they're still in vogue. They come and go. They're an old invention, but it's every so often people rediscover them as groovy. Okay, and what it is wax in another oil of some sort or another fluid of some sort. In fact, it might even be water. It's an oil that the wax does not mix with, so it probably is water. And the point is that when you heat up the wax, first of all, I should say the wax and the water have almost the same density. And therefore, the wax and water, they almost can float in one another. Not quite. When the wax cools off, it begins to turn into a solid. You're used to wax as candles or something like that. If you heat it up, of course, it melts. And when it solidifies, like nearly everything else in the world, it becomes more dense. So Most liquids are less dense than their solids, which means the solid sinks in the liquid. The oils, of which wax is essentially a member of, salt, sugar, anything you can think of with one exception, and that is water. Everything else but water, the solid sinks in the liquid. Is that okay? Lump of steel sinks in liquid steel. Lump of whatever. And so when the wax begins to solidify as it cools near the top of the lamp, its density increases, and it suddenly loses it's no longer buoyant. It is being supported by the fluid around it, but not enough to support its weight, and so it descends. And when it descends, it encounters a light bulb that's hot, it heats up, it turns back into a liquid, predominantly a liquid, and it becomes lighter than the fluid around it again, and up it goes. So it's endlessly cycling between going up, cooling off, and trying to become a solid and sinking, and then becoming a liquid and floating, and back and forth. Is that okay? I mean, the physics of that isn't the important thing. In this context, the important thing is you're getting all this motion. Stuff is moving around, and you couldn't conceivably do work with it, which is to say there's useful energy here. It's not a lot of useful energy, and it's not very useful, but the idea is there. It's moving around and sort of doing things, and yet the only energy present to speak of, to work with, is thermal energy. It's hot at the bottom and cooler at the top. That's all you got. Is that okay? And so if it's all thermal, so in this context, now I'll play with the other ones, and the other heat engines in a minute. But in this context, the big picture issue is all you've got is thermal energy. And based on a lot of what I've said up until now, you might think, well, gosh, if all you've got is thermal energy, which is it's the trashiest, lousiest version of energy available, how can you possibly undo the trash aspect of it and get it back to do anything useful? And the answer is that thermal energy by itself is useless. But if you have thermal energy in two different objects and they differ in temperature, now you've got something to work with. Because the law of entropy would prefer these two objects to have the same temperature. That's going to be the maximum possible entropy they can have. Let the heat flow from the hot one to the cold one until the two are completely identical temperature-wise. That's the end point you can't do anything with. But if there is a difference in temperatures, there's something to work with. There's little order left in it. Having a hot object and a cold object, that's inherently a little orderly. And that is what allows you to divert some of the heat that's flowing from the hot object to the cold object and turn it into work. Is the order present in two different temperatures. So here are two different temperatures. So after going through what I most wanted to point out with respect to the lava lamp is you can do with the physics a whole lots of things that are sort of complicated. They have more than one kind of physics in them. This is the physics of buoyancy and stuff and fluids. Hey, you can do that. And it's also the physics of thermodynamics, of heat flowing from hot to cold and turning some of that heat into work. So here's another one. As the holidays show up, one of you guys, a student some number of years ago, brought this one in. This is another heat engine. So I think I've got it. I can zoom in on this guy. What are my chances of remembering? Small unless I carry something around with me. So, you can watch this guy go around and around. So what's turning that? The little carousel on the top, and in principle ringing the bells, although I can't hear them myself, and you probably can't at all. It's a heat engine. The only energy we've got to work with here is thermal energy, because we're starting actually with chemical potential energy in the candles, But the first thing that this little gadget does is burn the candle as a flame, and now you've got thermal energy. And yet, thermal energy is able to do, in quotes, useful work. I mean, this is just sort of the physicists speak, but this is clearly driven by convection. The hot air is buoyant in the cold air. The hot burned gas, in particular, is buoyant in the cold air. Up it goes, and it's running a little turbine there at the top. Yeah, we can do the aerodynamics of that thing too, right? There's airflow on both sides of those little fins, and high pressure, low pressure. I'm not going to do it. Sorry. Okay, so another case where heat really is flowing from the hot burned gas above the candles into the room. So we're taking advantage of the fact that the room air is colder than the candle flame, and between the two of them, they can do something supposedly useful. Next thing to look at, we've got a little steam engine here, and the steam engine was, of course, one of the most important of the heat engines in the 1800s. All right, so there's a flame under here. It's technically what's known as an external combustion engine, because the flame is occurring outside of a boiler. And so the goal here is to heat up the water until the water boils, at which point we'll have steam, and we'll have steam not just at atmospheric pressure, but it's actually, the boiler is somewhat sealed, and therefore the pressure will build up above atmospheric pressure, and yet it will still boil. This always takes longer than I'd ever want, but we'll let it go for a second. And once you get hot, high-pressure steam, that's the hot object in the heat engine. The cold object in this case is the room, which is room temperature, obviously. In many heat engines that are based on steam, they want something more than just the air as the cold object, so they will use a lake or some body of water. They also will use cooling towers. So steam engines have not gone the way of the dodo bird. Steam engines are still around all over the place. They're used to generate electricity. Most of our electricity is ultimately generated still, certainly that using fossil fuels, is generated using heat engines based on steam and water. So they'll boil the water, even nuclear power plants. They'll make high pressure steam, which will be allowed the heat will flow from that to the outdoors or to the water or to some cold object. And in flowing from hot to cold, some of it will be diverted and turned into work. And in this case, it's a piston and cylinder arrangement. It's starting to boil. It's the famous watched pot. And it's rigged up so it's got a little hammer, as though it were genuinely doing something useful. We are on? Yeah, we're on it. Okay. And it needs to be nudged usually to get it to get started. No, not boiling yet. I'm going to turn off the candle one, just because we don't need to have to go forever. All right. I'm never sure which way this guy goes. Oh, it does want to go this way. Oh, come on. I'll start talking about something else and then it'll go. I'm going to zoom away from it. What I want to do is I want to talk about the last of the bunch. Camera home. Okay. So 3 heat engines. The steam engine will go eventually. And the steam engine, is there in part because it's such an important part of, certainly of the 1800s in that form. In the modern forms, the steam engines don't look like this anymore. The steam engines used to be railroad locomotives. They were all steam engines. sort of any power plant at all was a steam engine essentially of that type, heated either with some gas or with coal or something, wood. The modern steam engines, instead of being a piston cylinder operation, they're turbine systems. So they blow high pressure steam through veins, essentially like this little guy, and cause it to begin spinning. But they're much more high tech, and they are wings on that spin around. So they're spinning wings. It's a propeller run backwards with all the sophistication and aerodynamics that we talked about in the context of airplanes and the like. So steam engines are still widely used. The last of what's technically a heat engine is Dippy Duck here. And Dippy Duck, is Dippy Duck dipping? Dippy Duck sort of stopped. Let me get Dippy Duck going again. Once Dippy Duck has dipped his head once in the water, he should dip again in a minute. Let's watch. Is he going to do it? Come on, Dippy. Ah. Dippy needs a little help. There. Okay. What was I doing? Wake me up, right. Okay. Once Dippy gets going again here, the idea is this, that he will dip his head in, get it wet, or keep it wet, which is why I dunked him, and then he'll pop up normally for a while, and then he'll tip over again. And there he goes. Okay, he dipped his head, got wet, now he's back. He's functioning again. He sometimes needs to be woken up. The physics behind this is all about, the detailed physics is all about liquids and gases, and that the balance between landing and leaving. Can I zoom in on Dippy Duck here? Probably. I might have to. I will do it and move around. Let me show you Dippy Duck, because it's kind of fun, and the steam engine is just not going to. It doesn't want to steam. Where's Dippy Duck? There he is. Ugh. Operator error here. There we go. Okay. You see the fluid, that blue fluid that's in him? And I'm calling it a fluid because it's going from gas to liquid and liquid to gas. When his head is cold, which it is when it's wet, when his head gets wet, even though everything is at room temperature, when his head gets wet, water evaporates from his head. And that's a statistically driven thing, ultimately. Water landing and leaving could be in balance. If the room were entirely at equilibrium in every possible way, there would be no evaporation going on, no condensation going on, and Dippy Duck would be unable to do anything. However, the room air is relatively dry, and therefore, at room temperature, water molecules leave the surface of water more often than they land, and water anywhere around here is just naturally evaporating. It's evaporating from the top of that container because there's just not enough water molecules, the relative humidity is too low, to replace the water molecules that leave. So the water in the container is just gradually evaporating. The water on Dippy's head is gradually evaporating. And in order to evaporate, they need thermal energy to pay for the latent heat of evaporation. So Dippy Duck's head is cold. It's colder than his rear end there. And so the liquid is tending to evaporate in his behind and condense in his head. And as a result, there is a process that lifts the liquid up from his bottom to his head until his head becomes top heavy, and he goes from being in a stable equilibrium to an unstable equilibrium. Sorry, this is bringing like all of class, the whole semester is showing up here today. So he went from a stable equilibrium to an unstable equilibrium as his center of gravity went above the pivot. It's, you could write a thesis about this guy. Okay, so the fluid, he comes top heavy, tips over, and he takes a drink, and the fluid goes back to where it was because it just has a leakage catastrophe through the pipe that is his body. So you see the liquid just slurp down there. Anyway, so he'll sit there dipping repeatedly until he can't cool his head anymore for some reason. The water runs out, some aspect makes it, this thing's, is it ever going to go? No, I give up. Steam engine's not functioning today. Okay, so you okay with the basic mechanics here? I mean, that's not nearly as important as the fact that the Dippy Duck is consuming order. He's powered by order. As you can see, to start with, there's no initial temperature difference around. You can plop him down there with his container of water all at one temperature. Plop him down on the table, and he develops his own temperature difference by way of evaporation. He or she, I should be careful. I could even be broader. So it's really finally the thing that makes it possible for Dippy Duck to do its trick is the presence of order in the world around it. It's consuming that order, and the order that it's really consuming. I'll come back to center and stop. Turn up the lights. Is the order in the room that there is liquid water in the container and relatively low humidity in the room. That's an orderly arrangement. It's not the most disorderly, the highest entropy possibility. The highest entropy possibility when you've got a basin of water and dry air. That's not it. The most high entropy version is when the basin has evaporated to the point where the room air has so much moisture in it now that they're in equilibrium, that the landing and leaving match each other. And at that point, nothing further, there's no further evaporation from the basin or condensation into it. That's the highest entropy situation. Is that okay? This is right out of the problem set that will be ahead of you. And the way you can sort of, again, to use this, a scheme that I often use to describe how you can see the evolution of disorder and the increased disorders is take photographs of it and look at them in order. If you take photographs of a basin of water, or just like this container of water sitting there and the room air being dry, take a photograph, click, okay, and without letting anything enter or exit the room, so it's thermally isolated. Wait a day, wait a week, take a picture again, take a picture again, take a picture again, and then take the pictures, and even if nobody tells you what the order they're supposed to be in, you can order them. You know from experience that a container of water sitting there full in a room full of dry air, that's never the end result of a long series of waiting. It's the start. And as you go deeper into the collection of photographs, there'll be less and less water in the container and more in the room air until finally the container will have hit a certain level at which and it will stop changing. Why? Because the water is returning just as fast as it's evaporating. There's no further evaporation. The humidity in the room is 100% now. This container probably doesn't have enough water to achieve that, but a bigger basin would. All right? So this is a highly ordered arrangement. You got the water in the container, the room air is dry. That's not the end result of letting entropy build. Okay? So that's all my heat engines to play with. They're all, they're chewing up order to do something. Most of them by way of moving heat from a hot object to a cold object, which chews up order. So how about an automobile engine? How does an automobile engine work? It burns the fuel, whatever the fuel, whether it's gasoline or whether it's diesel fuel. It burns the fuel as the first thing it does. This, incidentally, may change during your lifetime. That act of burning the fuel, burning the gasoline, for example, in your car engine, destroys so much order, and which is then has to be tried to be resuscitated. It's terrible. You can do much better if instead of burning this chemical this fuel and with its chemical potential energy, you very strategically let the fuel and oxygen in the air react with one another in some controlled situation and use it to generate electricity directly. And devices that do that are known as fuel cells as opposed to electrochemical cells, which are batteries. You're used to batteries now, and the batteries have gotten amazingly better over your life, even in your lifetime. I mean, you're now used to having batteries that stay charged for ages, and it's phenomenal what has developed in the past half century in the way of batteries, and probably following on the heels of this will be fuel cells. And the advantage of a fuel cell is that instead of the battery just being a specific object that you charge and then you later discharge, and then nothing ever changes about the object. A fuel cell, you actually can bring chemicals into the it's like a chemically powered battery where you bring in fresh chemicals whenever you like. And so you could, before you take a long plane flight or something like that, you might just give a squirt, just a little dose of chemicals to your laptop, and it's good for the flight. You don't have to recharge it. You just add chemical potential energy directly. And the same with cars. It's conceivable someday that the cars will be fuel powered instead of battery powered, but the fuel will go into essentially a fuel powered battery. So you put it in, it derives essentially all of the available energy that showed up as chemical potential energy will leave this fuel cell as electric power, electric energy, and be usable by the car. Okay, so after that harangue, what's the point? The point is that automobiles burn the fuel and air, and in doing so, they immediately lose about half the useful energy. They can still get back a certain amount of work out of this, but they only get about half of what they could if they didn't burn the stuff. All right? So how do they get any energy out after burning it, right? It's thermal energy again they've created. Terrible choice. The way they do it is they let heat flow from hot to cold and divert some of it under the umbrella of the law of entropy. They convert some of it into work. And they're limited in how much they can convert. And the hotter the high temperature and the colder the low temperature, the bigger the fraction they can convert to work and not violate the law of entropy. So a car engine wants to burn the fuel and air to the highest possible temperature, and they want to work in cold air outside. So in principle, cars become more energy efficient at low temperature. This is in principle. In practice, there are other issues like when it's really cold, everything doesn't move very well. So that's unrelated to thermodynamics. It's a different problem. But anyway, they want to burn the hottest hot they can get, the coldest cold, let the heat flow from hot to cold, and divert the largest fraction they possibly can, limited by the law of entropy. So that's what they do. And the two classic types of engine are the so-called internal combustion engine, which is synonymous with gasoline engine. That's one. The other is a diesel engine, which is very similar in many ways, but with one key difference. So let me walk you through the way in which an internal combustion engine works. You okay with the big picture view of it? The physicist view of it is it's a heat engine. Set that aside. Let's go to sort of the mechanics view of it. You might as well know how an internal combustion engine operates, because it's for sort of the foreseeable future, it's going to be part of your life. An internal combustion engine, gasoline engine, is a four-stroke engine, which means that within the engine it has a number of little energy work-producing elements, which consist of a piston and a cylinder. It has several of those, typically 4, 6, or 8. And each of those little energy-producing elements, the piston and cylinder, go through a sequence of 4 steps repeatedly. So four distinct steps, and then it repeats. 4 distinct steps, and it repeats. And the steps are called strokes because there's movement involved in these steps, and the movement consists of a piston moving in or out of a cup, which is referred to as a cylinder. yeah, so you get a good view of nothing. And why is there nothing there? It's because the power is off. I love it. All right, so in a minute or two, we will have, the screen will come back on. So the idea is this, that there's a piston that will move in and out of this cup-shaped cylinder with there's some valves in the cup-shaped cylinder. And it goes through, it goes through an out motion, which is called an induction stroke, an in motion, which is called a compression stroke, an out motion, which is called a power stroke, and an in motion that's called an exhaust stroke, and then we repeat. So this is going on in your engine, and it occurs dozens or even many dozens of times per second when you're really moving down the highway. The motion is fast and furious. It's astonishing that this all works and continues to work for months and years. All right, so this is the induction stroke. So I'm going to show you 4 strokes. And so this is, whether this is physics or whether this is just tools for a living, I don't care. The point is that you might as well know what's going on inside the engine. So your engine typically will have 4 of these cylinder piston pairs, or 6 of them, or 8 of them. And there's a reason for having more than one. I mean, you could make a car with one, but it's got some problems. Okay, during the induction stroke, the piston moves out of the cylinder and creates a partial vacuum in the region that's confined between the piston and cylinder. So this is a trapped volume that is being made bigger. And as it does, the pressure drops below atmospheric pressure. So 2 things about that. One is because the pressure drops, because it's being produced below atmospheric pressure, this piston has to be pulled out of the cylinder. It doesn't come out for free. So the engine is actually doing work on the piston when it's doing this induction stroke. This costs the engine. And this is one of the reasons why you need more than one cylinder, is because during this motion, the engine's got to come up with mechanical energy from somewhere. Where's it going to come from? Well, there are many sources available, including the car's overall motion, but actually it also can come from another cylinder piston pair that's producing power. So that's why you want to have more than one cylinder piston pair in the engine. Okay, so the piston is being pulled out, making an empty space here, and a valve is open to let air go in. So air is being sucked into the engine during this stroke. And it's not just air in an internal combustion engine, it is also fuel. And in the old days, the fuel would come in with the air. The old, what were known as carbureted cars. So if you get an antique car these days, you might well have a carbureted engine and the fuel and air going together. In modern cars, there are no such cars being manufactured these days. Instead, the air goes in, and at the same time, there are fuel injectors that take very high pressure liquid gasoline and shoot it through a pinhole. And it atomizes as it comes out. It's just a little jet of liquid that breaks up into little droplets and evaporates essentially instantly into the air. So modern cars are fuel injected. They have, it used to be you drive down, you see a car would proudly tout the fact that it's a fuel-injected car, but now they're all fuel-injected cars, so therefore it's boring. So you never see it anymore. But so air and fuel go in there, they mix, they evaporate as best they can, and now you've got a mixture of vapor, fuel and air at the end of the induction stroke, occupying that big open space within the piston cylinder pair. So far, so good? All right, next stroke, the compression stroke. And the compression stroke is the reverse of the piston moves the other direction now. It's pushed back into the piston, into the cylinder, and the valves are closed during at this time. So the gas is trapped inside there, and it's squeezed by the piston. And the piston's doing work on the gas. So the gas is being squeezed, so its density is going up, its pressure was certainly going up. What's happening to its temperature? What do you think? If you're doing work on gas, what happens with temperature? Temperature goes up. So as you squeeze the fuel-air mixture, it goes to higher density, higher pressure, and higher temperature. All right, I'll come back to the higher temperature shortly. At the end of the compression stroke, the fuel-air mixture is compressed to it's packed really tightly up at the top of the cylinder, right near an object known as the spark plug. So that's the spark plug sitting up there. And it's hot too. So that's the end of the compression stroke. And now the power stroke. And right at the beginning of the power stroke, the spark plug fires up, makes a spark, which is a whole nother story, and I won't years ago I used to do it, but I'll leave it aside. How do you make a spark? What is a spark? It ignites the fuel and air mixture, which burns almost instantaneously. But it really is a burning process as opposed to an exploding process. So flame shoots through the whole thing in like less than 1,000th of a second. But it all burns, hopefully to perfection ideally, but in practice it's not quite perfect. And now you've got a hot burn gas. It was already high density and high pressure and high temperature. Now it's really high temperature, 5,000 degrees or something like that. And the pressure's enormous, way more than it was before the burn. And because the gasoline has been chopped up into little pieces, little molecules, actually the particle density has increased dramatically. And so that's additional cause for an increase in pressure. So the pressure is way up there. And during the power stroke, that extremely high pressure gas pushes the piston out of the cylinder and does work on it, does a lot of work on it. This is it's called the power stroke because this is where the engine gets its power. The previous two strokes were both losers for the engine. Sucking air into the cavity in the induction stroke, it's a loser for the engine. Compressing the air in the compression stroke, a loser for the engine. It takes work. This one is a winner for the engine. The gas does work on the piston, shoving it out. And the last step is once the piston gets as far out as it can physically move, they open valves at the top of the cylinder that let the hot burn gas, which is still there, let it out. They squirt it out, and it's just the exhaust stroke. So the piston comes back into the cylinder, squeezes out the hot burn gas, and goes out into the great outdoors eventually, and you're ready for the next induction stroke. You okay with any questions about the four strokes? So what does thermodynamics and the heat engine stuff have to say about this? Well, at the end of the power stroke, let me just flip back to it. Maybe this is a better picture. At the end of the power stroke, what's in that cylinder before you open up the valves? And the answer is it's still hot gas that is above atmospheric temperature, ambient temperature, and it's above atmospheric pressure. There's more, it could still do some work. Why are you wasting it? Why are you letting it out? Well, it actually can do a little more work, and there are engines that let the piston come out farther during the compression stroke, the power stroke, than any of the other strokes effectively, to try to eke out a little more work out of it. But there is no way you can actually get the gas to drop to atmospheric pressure and ordinary ambient temperature. It will never happen. There's no arrangement of where the piston is that will achieve that. And that's the law of entropy covering its butt. You can't do it. You can't take if it were possible to get the piston out just to the point where the temperature drops to room temperature. And the pressure inside is atmospheric pressure. Wow, it's great. You can open the valve and just squirt out gas that has no extra thermal energy in it, no more than you could possibly get out of it, and no extra ability to do work. You can't do it. No matter how you play with the piston and the cylinder, you're inevitably going to have to either release the gas still hot with thermal energy in it, or you're going to have to actually do work on the piston, pulling it further out of the cylinder to cool the gas down to room temperature. You can't get everything you want. And so inevitably some of the gas comes out hot. And that's it's a heat engine. You don't get 100% of the thermal energy as work. You get part of it. And the other part, it's got to go out in the great outdoors. So this is why cars have radiators. That's part of the system for getting rid of the extra heat, the heat that you can't use. You're forbidden from using it by the law of entropy. The best you can do is try to burn the fuel and air as hot as you possibly can and get the biggest fraction you possibly can out of the stuff before you kick out the waste heat. Incidentally, when the valves open on the cylinder right at the beginning of the exhaust stroke, as drawn up here, the gas inside the cylinder still is well above atmospheric pressure. And when you open a container that's well above atmospheric pressure, it goes pop. So this is the pop, 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 pop you hear of engines going by, particularly like under-muffled engines like motorcycles tend not to be well muffled. Your cars all have mufflers in them. If they don't have, sometimes a muffler goes bad and becomes effectively nothing, and you know it because you hear the car is just really loud. It's I can't imitate it, right? Okay, but it's that pop 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 sound. That's the cylinders opening and letting out the high pressure gas. And so what a muffler does is it just tries to smooth out that pop 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 into a whoosh by sending it through a whole series of baffles. That wastes a little bit of the engine loses a little bit of energy efficiency, but it's tolerable sound-wise. All right? So that's the four-stroke engine. What I want to tell you about this? Let me flip back. I will actually go back to the compression stroke and remind you. The compression stroke involves squeezing the fuel and air mixture and doing work on it. And its temperature surges upwards. And what happens if the temperature goes up like that too high? Well, you can ignite the fuel and air mixture. How come you have to add oil to four-stroke engines while two-strokes don't need it? The oil in an internal combustion engine acts as a lubricant and a coolant. It's not inside the cylinder, the fuel and air mix. It's not inside the trapped volume. So when you get an oil change, the oil that you put in your car, that bathes all the mechanical parts of the engine to keep them so that they can slide with as little friction as possible, and certainly with as little wear as possible. You don't want things wearing out. And so that's present in it's not part of the burning process. It's used in it's essential to all of the strokes, all the movement. That cylinder and piston moving together would rub like crazy were it not for oil between the two, so that they can slide relatively easily. Okay, but with the compression stroke, the issue is that fuel and air mixture can reach very high temperatures as it compresses. And if the fuel and air ignite in the presence of that high temperature, you have a problem. The engine pre-ignites. It's called pre-ignition or knocking. And the engine the fuel and air mixture don't wait until the piston has reached the bottom of the cylinder. And so the last part of the compression stroke has to fight this enormous surge in pressure. And it just shakes the whole engine. It's hard on the engine. It's wasteful of fuel and air, wasteful of gasoline. And so I want to show you that concept of knocking or pre-ignition. The idea that it is possible for a mixture of fuel and air to ignite not because you fired the spark plug, but because you compressed the gas so tightly, so fast, that the temperature surged upward. Is that okay? So this is a little cylinder, it's a plastic cylinder into which I can put a little piece of cotton. So the cotton's now at the bottom, and I will put on a piston. And what I'm going to do is I'm going to compress the piston by hand. It's a little piston, so I can shove the thing down there. And as I shove it down there, friction isn't the issue. It's not going to get hot because of friction. It's going to get hot because I'm going to do work on the gas, and the gas's temperature is going to skyrocket, and it's going to ignite the paper, the cotton. Is that okay? So it's a brief flash, and we can do it more than once. But ready, get set. Okay? And that's, it's fun, but it's not what you want to have. So there's another piece of cotton in there. This is not how you want to run a normal car engine either. It's kind of slow. So again, as I compress it, the temperature will surge upwards. You're way into the 1,000-degree plus range. Ready, get set. All right. Apparently somebody years ago put a whole lot of that, the stuff in there, punched on it, and it exploded. Yes, okay. So the knocking process is when the fuel and air mixture compressed like that just bursts into flames, it just burns, and doesn't wait for the spark plug. So the solution in an internal combustion engine is to be careful with the compression process to make sure you don't over-compress it. So engines are designed to have a certain compression, no more. You don't want to squeeze the fuel and air mixture beyond a certain point because you will ignite the fuel. The other way in which you deal with this is by choosing the difficulty to ignite the fuel, which is known as the octane number. So when you buy different octanes of fuel, you go to the filling station, and it lets you choose 87, 90, 93 usually, octane, whatever the heck that is. You know, they're also as regular, mid-range, and premium. You know, what are you buying when you buy those? Essentially, all you're buying when you're working your way up that list is difficulty to ignite. And that is, in a sense, the ability for the fuel to tolerate the compression stroke. And most cars are designed to not accidentally ignite regular gas. And if your car is one of the most cars, if your car's like that, buy regular gas. Putting premium gas into it is not pampering your car. It's just you're just burning fancier stuff, and just it's of no consequence. Therefore, if your car runs on regular, buy regular. Don't, you got the idea? You understand what the premium gas, there are cars with high compression engines that need that extra hold off on the ignition so that they can operate on, they have to operate on premium gas. But for most of us, that is not our car. Right? Last thing to show you, you go out with a bang. What is it like to ignite a mixture of fuel and air in a confined space? So you might as well go out like that, okay? So this is, I'll do it like this. Oops, overshot. Okay. So this, not gasoline, it's methyl alcohol, which is pretty similar in terms of how it burns. So I'm making a fuel and air mixture in here. Of course, I'm taking my time on it as opposed to a car which only has 1,000th of a second to do it. And the spark plug is that guy down there. And if I put it on lightly, which I just did, it should fly up in the air and not go kabang. So let's try that first. Ready, get set. Okay. That was the simple combustion. If I shove it on tight, though, it'll go kabang, and that's why I have the earplugs. Now really crunch it down there. All right. Ready? Ooh. Okay. With that then, they've been better, but that's good enough. With that then, have a good break and see you on Monday.